Okay, so this is the second part of the video on periodic trends, and I already explained what you have to know, which is what are the trends, why they happen, and what do they mean. So in the first video, I explained all about atomic radius, ionic radius, and ionization energy, and I will use the rest of this video to explain about electron affinity and about electronegativity. These are quite simple to grasp. I explained before that ionization energy is the energy needed to remove the outermost electron from a gaseous atom, and now we know that the electron affinity is the energy change that happens when an electron is added to a gaseous atom. So right here I have an example where there are electrons and they're trying to add this extra electron into the orbital, and the energy change will be most probably and most commonly a negative value. So when explaining the trend, we can see that you have a neutral atom of chlorine, for example, and you're adding an electron to make it an ion. And this is going to be an anion, as I explained in the previous video, because anions are negatively charged. So we are adding an electron to the neutral atom, and this will give you a negative value most commonly. So things to keep in mind, which is quite similar to things to keep in mind for ionization energy, is that atoms want noble gas notation, and they want to get there as fast as they can. So this is the charge and common charge table that I keep referring to, and basically it states that lithium, for example, will want to form a positive 1 charge to get to noble gas notation, and fluorine will not want to form a positive 7 charge and lose 7 electrons to get to helium. It's just a lot faster to go from full fluorine to neon and just gain 1 electron and become negatively 1 charged. So what are the trends for electron affinity? Across a period, it will increase, which means that it will become more negative. So as you move across a period in the periodic table, they will become more negative. So for example, fluorine has an extremely negative electron affinity value, and the reason for that, and which I explain here, is caused by the electron repulsion in the outer shell. So if I refer back to this drawing, we can see that there's a number of electrons right here. If I try to squeeze in another electron, there's going to be repulsion between them, and that repulsion is going to release energy. So that's why it is the most negative when it is the furthest to the right of the periodic table. And down a group, it'll decrease, which means that it will become less negative. And the reason for that is because there are more outer shells, and so there is not that much attraction to the nucleus, and there is not that much repulsion between the electrons. So when dealing with electron affinity, remember that across a periodic table it will become more negative, and down a group it will become less negative. And the big one that we really have to know, and this is extremely important because in chapter 4 we're going to discuss a lot about bonding and whether it's a covalent bond, ionic bond, and it is a lot based on electronegativity. So electronegativity is the measure of the pull of an electron towards an atom within a bonded pair. So we know, as we can see in this example over here, when there are 2 bonded atoms, we know that, although it sounds counterintuitive, that the electrons on one side will actually shift to either side depending on electronegativity. So here they make the analogy with tug of war. So it's the idea that if both players are equally strong, which means that they have the same electronegativity value, then the electrons will stay in the exact middle. If one player is stronger, like this red one over here, and competing against a weaker player, the stronger player will actually be able to pull the electron closer. So the electronegativity value, if you think about it, is just how strong an element is when playing tug of war against another, and the prize would be to pull the electron closer to them. So this happens only between bonded atoms, which is extremely important to remember, and bonded pairs can actually steal electrons from one another. This is what happens in ionic bonds, which you will see in chapter 4. So it is important to remember the strongest will win. So the value or the atom that has the strongest electronegativity value will pull the electrons closer to them. So what this means, this is extremely important. The smallest equals the strongest. So fluorine is actually the smallest atom that we have, because it has the largest Z effective, as I explained in the previous video, and therefore the outermost electrons are the most attracted towards the nucleus, and it makes the entire atom extremely compact because of this attraction between the nucleus and the outer electrons. Because of this attraction, the fluorine atom, which is the most electronegative, and it is 4.0 negative, will be able to attract the electrons closer, because the electrons will actually feel the pull of the nucleus of the fluorine. So what is the trend for ionization energy? It'll increase across the period. The closer you are to fluorine, the more electronegative you are. So lithium is way less electronegative than fluorine, and so is beryllium. Between oxygen and fluorine, you won't. But if you were to have a bonded pair between those, the electrons would still shift towards fluorine. And it'll decrease down a group because firstly, you're getting further away from fluorine, and also because as you increase more and more shells, you will have less attraction towards the nucleus, which is what we explained in Z effective, and therefore will be less able to attract electrons from the outer shell and pull them closer. So fluorine is the most electronegative, and the elements around it will also be quite extremely electronegative, remembering that electronegativity is measured on a scale until 4. So those are all the periodic trends that you need to know and their explanations. Be sure that you know how to explain them. A lot of multiple choice questions will have that. And remember that the effective nuclear charge is the way to determine most of those trends, and it's basically how many outer electrons there are. And you count outer electrons by 1, 2, you skip all the transition metals, 3, 4, 5, 6, 7. The more there are, the more the electrons are attracted towards the nucleus. So that's the periodic trends video.